Good morning, aspirant. Hope you all are doing well. Your days are going productive and you are doing excellent in your studies. This lecture actually I have recorded a few hours back, but after the recording, I am just when I'm going to the files, then I am not finding the file. Okay, maybe it was not recorded or something technical glitch. So it's very disappointing for me also. I will explain each and everything, but the slide will remain like this. Okay. Now just listen to me looking at the slide. Uh, Suppose I have a pen. I have a pen. The primary purpose to make this pen was to write something. But suppose I am going uh, into a street, through a street along, and few criminals approached me to snatch my mobile phone from me. Then the only option for me is to use this pen as self-defense. Similarly, inherently, this operator concept was not a part of quantum mechanics. It was a mathematical tool. But if we want to use this mathematical tool in quantum mechanics, we have to mold it, we have to modify it a bit, or we have to mold in such a way that it is applicable to quantum mechanics. Okay, the same thing we will discuss here, where the operator, when we want to use this operator in quantum mechanics, and we will take from mathematics and we will use it in quantum mechanics, then the operator must be linear. The operator must be linear. So that means in quantum mechanics, only linear operator matters. Only linear operator matters. So the statement is, operators in quantum mechanics must be linear. Operators in quantum mechanics must be linear. Okay. We were just studying operators and we were looking at few properties. Like fourth property was few observables in classical mechanics. Fifth property was commutator. Then we have seen its property and its numericals. From numericals, we have derived some formulas. And it is the sixth one. So sixth property says operators in quantum mechanics must be linear. That is, it must satisfy the following. This condition, if one operator follows this condition, then only we will call that operator a linear operator. What is the condition? Let's understand it. Suppose I have one constant C. Suppose I have one constant C and I have into one function f of x. And another function is linearly joined. Linearly joined means in addition or subtraction. Linearly joined. It's not a power or multiplication. I have one constant d. I have another function, that is f dash x. F dash x is just another function of x. It is not the derivative of x. Suppose now the addition of two functions, it is also definitely a function. So if I operate my operator on this, if it keeps the c constant out and just directly operate on f of x. Similarly, plus d is a constant, it does not operate on constant, so it keep it outside and direct operates on function. If my operator does this, then I will call my operator a linear operator. So linear, for being linear operator, what should you do? Linear operator do not operate on constant, right? And linear operator operate additively on two functions that are linear. Two functions are linear, that means plus or minus, joined by plus or minus. These are linear. Then linear operator will operate additively, that means as it is. If it is plus, then you will add. If it is minus, then you will minus it, subtract it. Okay. If there is minus, there will be minus. Okay. So these are two conditions of for being some operator, a linear operator. My question is, let's say ddx operator is linear or not. Let's check ddx operator is linear or not. To check it, let's take a random function like this. For example, the value of c is 3, f of x is x square, d value is 5, f dash x is x cube, and my operator a is ddx because we are checking ddx. Now let's put the value here. C is 3, a is ddx, f of x is x square, plus d is 5, a is ddx, and f dash x is x cube. Is the condition true for ddx? We will say yes, this condition is true for ddx. That means ddx is linear operator. Okay. So to check linear operator or not, you just take one such function and operate with your function. Operate your function with that, and if you get the result, then you will say that it is a linear operator. You can just simply take, for simplicity, you can just only take this function only. If operator of constant a, let's in the next no, okay, if my operator constant a is on function f of x, if it is giving a operator f of x, then also we will call it a linear operator. It is a simplified version of this, only this part or only this part. Okay, so if this part is linear operator satisfying the condition of linear operator, this part will also do. So to check it is linear operator or not, just use this part only. With this, I have the question for you. Let's solve. Identify the following operators are linear or not. Integration is linear operator or not, square is linear operator or not, sqrt square root is linear operator or not, log linear operator or not. So suppose my function here is 5x square. If my function is 5x square, so my 5 is constant, my x square is function. First put integration operator on it. Can I write it that 5 will be outside, then I will have my operator, then function. If I can write this, then it will be linear operator. Yes, we know the rule of integration that we can write it like this, but let's check for a square. 5x square. Will this square operate on 5x? 5? Can you write it like this? Of my constant will be outside, and the operator, this third bracket and square, that is square operator, will operate on x square. This is not true, right? This is not true, we know that, because actually the solution comes 5x square. Similarly for root, square root, do we solve normal square root like this, that we keep that constant outside, and we operate this with function only? No. So this is also not linear operator. Similarly log, we do not write like this, so this is also not linear operator. So only this linear operator. So till now we have known two operators, we know these which are linear operator, that is integration and differentiation. Integration and differentiation are linear operator. Now few points, you have to write few points on operator. Our last part on operator is few points on operator. Few points or few properties, few extra things of operator. First thing is, linear operator always commute with constant entity. If any operator is linear, it will always commute with a constant entity. Let's see. Suppose a is my linear operator, small a is constant, and psi is my function. Now my statement saying that linear operator and the constant will always commute. To check if they commute or not, we have to write them like this: commutator, a operator and a constant. If it is 0, the result is 0, then we will say this will commute. If it is not 0, then we will say it will not commute. Now let's check. Let's prove it. Let's take its commutator. I have taken the a commutator and psi is my function. and we have to write this AB minus BA form, A comma B. To simplify the commutator, we have to write AB minus BA of psi. Now, a constant can be outside. Constant can be outside, okay? The A operator will operate only on psi. It will not operate on A. So, A will not operate on A. You will operate on psi only. So A will go outside. So we can write A like this here and here an operator. Minus similar here. So A psi minus A psi. It will be 0. So that means they commute with each other. Okay. So first property you have understood. Second property. See, the first property was property of linear operator. If my operator is linear, then only this condition satisfies. Okay, for any linear operator. Second property is any operator commute with itself and its power. Any operator commute with itself and its power. Suppose my operator is A itself and its power, that is A to the power n. These two will always commute. For example, A to the power n commutator of psi. Then A to the power n minus A to the power n A psi. Then this will be equal to 0. Okay. If they commute with each other, that means this is 0. If they commute with each other, then this will be 0. This 0 means A to the power n A psi equal to A to the power n psi. That means on psi, if A operate first, then A to the power n, it is the same as if first A to the power n operates, then A operates. So any operator commute with its self and its power. So for that, any operator A and A will be 0. A commutator A will be 0. A to the power n commutator A will be 0. A commutator A to the power n will also be 0. Okay, fine. Fine. Second property. Its implication. What is its practical implication? Suppose there are two operators, Tx, that is kinetic energy, operator corresponding to kinetic energy, and Px means operator corresponding to linear momentum. Actually, Tx operator indicates the kinetic energy component along x direction. Linear momentum, Px means linear momentum component along x direction. So do they commute with each other or not? Let's check. Tx operator, kinetic energy means, we know kinetic energy T means P square by 2m. That means kinetic Tx means Px square by 2m, comma Px. Will they commute with each other? Let's check. This 1 by 2m, this will be common, getting common. This will be getting common. We are willing to just simplify things. This will be get common like 1 by 2m. Why it will be getting common? If you write the whole thing as AB minus BA, for A part you will be getting always 1 by 2m, 1 by 2m. So from both you can take common of 1 by 2m. Okay. And what is remaining inside the third bracket? Px square comma Px. So here one function, its power and that function itself, they commute. So this will be 0. So that is 1 by 2m into 0. That means overall 0. So kinetic energy operator and linear momentum operator commute with each other. This is a very bold statement, very important statement. Okay, so kinetic energy operator and linear momentum operator always commute with each other. Okay. Third note. Two operators with multiplication as operation always commute. Two operator with multiplication as operator. Multiplication as operation always commute. I have discussed with you few operators, that is position, moment, linear momentum, angular momentum, kinetic energy, potential energy, total energy. Among all these operators, only two operators is there whose operation is multiplicative. That is position and potential energy. That is x. Position we can denote is at x cap or y cap or z cap. Potential energy we denote as vx cap or vy cap or vz cap. They commute with each other. So x will commute with y, x will commute with z, z will commute with x. y will commute with x will commute with y will commute with x, and Vx will commute with Vy will be Vz, Vy, Vx, Vz, Vx, x Vx, y Vy, z Vz, x Vy, x Vz, y Vx, y Vy, y Vz. Each and every component, each and every combination will commute with each other between these two operator. So if I have the position operator x cap, y cap, or z cap, or potential energy operator Vx, Vy, Vz, then x will operate with y, x will commute, sorry, not operate, x will commute. X will commute with y will commute with z, x will commute with z, Vx will commute with Vy, Vy with Vz, Vz with Vx, x can with Vy, y can with Vz, y can with Vx, z with Vy, x can with Vz, okay, Vz can with z can with Vx. So each and every component, they commute with each other. So these are very significant, very significant properties. Okay. Just I will be giving you two more properties. After that, we will be getting into numerical problems again. So three properties we have seen. Okay. Fourth property, x del x, it will be -1. Already we have solved this earlier. Y del y. If you do not if you do not agree with me that we can write it like this, so you can solve it. How you can solve it? X del x psi, that means x del x minus del x psi. So let's take psi. Let's take psi inside. X del psi del x minus del x of x psi. That means x del psi del x minus x del psi del x minus del x of x. This will cancel out, and minus of del x upon del x is 1. Del x by del x 1. That is basically -1. Okay, this will cancel out, will become 0, and minus of del x upon del x, right? That is basically -1. Z del z will be -1. So these are not equal to 0. So x del x do not commute. Okay. Now if we write it opposite, del x comma x, it will be 1, right? Del x comma x. Just if it do not commute, then we can reverse it and change its sign, equal to +1. Del y comma y, commutator will be +1. Del z comma z, it will be +1. Okay, but if the direction changes, then they will commute. If direction changes, that will commute. That means, suppose I am writing this position operator x, y, z, and here I am writing del x, del y, del z. Now what I have said, that x and del x, they will not commute. X and del x, they will not commute. Y with del y, they do not commute. Z with del z do not commute. But x and y will commute. Y and z will commute. This x and y will commute. We can also say that with the property of the previous one, that when two operators are multiplicative in nature, then they will commute with each other. Del x will commute with del y. Del del y will commute with del del z. Similarly, x will commute with z. Del del x will commute with del del z. Okay. So same direction do not commute. Opposite direction commute. Similarly, del del x y will commute. X del del y will commute. Y del del z will commute. Del y del z will commute, and each and everything. So this is the again this is the another significant property. And what is the practical implication of this property? What is the practical implication of this property? If we know that x and del del x do not commute, or x and del del y commute, first take this, let's say x and del del y commute, that means their commutator will be 0. So x comma del del y, it will be 0. Now if I write py, that means minus I h cross del del y. So x del del y if commutes, then x minus I h cross del del y will also commute, because this is merely a constant. That means x comma py will commute. That means x will commute with py, will commute with pz, but it will not commute with px. Similarly, y will commute with px, will not commute with py, will commute with pz. Sorry, will commute with pz. Okay. Will commute means commutator's value is 0. Will commute means commutator value is 0. Will not commute means commutator value is not equal to 0. Okay. Similarly for z. Okay. So these are, and this is another significant conclusion of the operator properties we have already seen. Now, five, two derivative operators. Two derivatives will always, sorry, two partial derivatives, these are partial derivatives, will always commute with each other. Commute irrespective of direction. Will commute irrespective of direction means del del x will commute with del del y, will commute del del x, will commute with del del x, del del x will commute of del del z, and each and every possible combinations of that. That means if del del x comma del del y commute with each other, that means its commutator value is 0. Okay. In the last slide, did I say something wrong here? X py will commute, that means value is 0, right? Commutator value is 0. Okay. That means minus IH cross del del x comma minus IH cross del del y will also be 0. That means px comma py will also commute with each other. So px, py, pz in any combination, they will commute with each other. Okay. Px, py, pz will commute with each other. Okay. So just I am consolidating the properties. Okay. From backwards, we are just starting the consolidation. Px will be 0. Px, py will be 0. Px, pz will be 0. Py, px 0 means px, sorry, py, px is 0. So there will be many equations. Just I am writing few things. px px 0, px py 0, px pz 0. That means in the same direction it is also commutating, in the opposite direction it is also commutating. This is nothing but ddx comma ddx is 0, and also ddx comma ddy will be 0. Okay, so same direction is also 0 commuting, and opposite direction is also commuting. This is 0, right? No problem. Similarly, we are saying that x del x, it is -1. But del x comma x, it will be obviously +1. But when I am writing in different direction, x del y, it is getting 0, right? Now, so x px, so x px, we have previously solved that, right? X px, maybe minus IH cross x px, we have already solved that. It is IH cross, right? X px is IH cross. Okay, okay. So, but it's x py, then it will be 0. Similarly for reverse, we will see it. This is another property. Then multiplication as an operator, x y will be 0, x x will be 0, vx x will be 0, vy x, it will be 0, right? Multiplicative as an operator, it will always be 0. Next, any operator x comma x to the power n, it will be 0. Any operator with its power x to the power n comma x, it will be 0, and x comma x will also be 0. So these are the set of properties we have seen here. So you have to practice a lot this, that when in mathematical, in any operation, you will be getting this. With next line you have to write it like 0. But when if you want to go that simplify it like px equal to minus IH cross del x comma minus IH cross del z, and after that if you are going to solve this, then that will be a very long solution. Okay, we will not go into that. So you have to recall your results. You have to recall these results, actually these basic results. They're very simplifying. The power rule you already know, right? Power. Then multiplicative, that is v comma x, position and potential energy. Any combination will be 0. Then two derivatives ddx ddy upon any direction, it will be 0. Upon any direction it will be 0. Okay, you may get confused in, you may get problem in like this. It is different direction is 0. That means in different direction they will commute. In same direction they will not commute. In same direction they will not commute. When they will not commute, you have to just remember the results. Okay, these results already I have made you write. Okay, for example, p to the power x to the power n comma x, this type of equations I have already shown you with all of this formula. If you recall it, then only in the next class you will be able to solve the mathematical problems related to overall operators. So I hope you have liked this lecture and meet you in the